Hi, this is Dr. Viv. In this video, we'll consider a number of problems, all of which share a common theme. In other words, there's a loopy or a hilly aspect to all of them. In the first problem, you have a particle starting from rest at a certain height r, and it encounters a hill of radius h. We are told the normal force at the top of the hill is just 1/3 its weight. And you asked to find the ratio of h upon r. In the second problem, a particle is released from some height h, again from rest, and then it acquires enough speed to barely make the loop. Barely makes the loop means it loses contact at the top point, which we'll call A. You're asked to find the height, the normal force at the bottom point B, and then when the particle encounters a frictional patch of length 3r, it comes to a stop at point B prime. You're also asked to find the coefficient of friction mu sub k. The last problem has a fixed hemisphere, and the particle is on top of that fixed hemisphere. That's a pretty unstable position, so it would either go to the left or right. Let's say it goes to the right, and then acquires enough speed at some point it will fly off the hemisphere. You're asked to find the angle theta when it does so. All these problems share a common theme, and that is you need to combine the Newton's second law for circular motion along with conservation of energy. So let's proceed by combining these two ideas and solving the problems. So let's go with the first problem. There, the sum of all the forces acting in the negative r hat direction is mass times centripetal acceleration. That's Newton's second law. Let's see how that would apply to this problem. You may think a good way to do this problem is to apply energy between 2 points, and indeed the 2 points we consider are going to be I, the initial point here, and the F, the final point here. But the problem with energy conservation is you don't know the speed here, and you don't know the height. So you have two unknowns, so one equation cannot give both of them. Therefore, we need another equation that would be provided by the conservation by Newton's second law. Let's draw the free body diagram at point A. The normal force is over there, and the force of gravity is down here. I've purposely drawn the force of gravity to be bigger because I need the centripetal acceleration at point A to be pointing downward. So the Newton's second law in the radially inward direction gives me mg minus the normal force at A equals mv squared mva squared upon h, the radius at that point. And I want to thank one of my subscribers who made this correction. I initially had written mv squared over r in the first generation of this video, and he kindly pointed out it was mv squared over h, so thank you. Mg minus normal force at A is given to us, which is 1/3 mg, is equal to mva squared upon h. Now 1/3 when subtracted from 1 is 2/3. What I will now do is multiply both sides by h. So I get mva squared equals 2/3 times mg h. Normally you would solve for speed, but I won't do that. I'm only interested in the kinetic energy, which is 1/2 mva squared. So that gives me 1/2 mva squared is equal to 1/3 mgh. I will call this equation 1. This relates the speed to the radius of the hill. Then we have chosen the points I and F, which is very important to do in energy conservation. I'll apply the total mechanical energy at I equals the total mechanical energy at the point F, which is A. There's no spring in this problem, so it's just kinetic plus gravitational potential equals initial equals kinetic plus gravitational potential final. In all these problems, it's useful to take the reference gravitational potential energy to be 0 at the bottom. So I'm going to do that for all three of them, so I don't have to do it again. It's just a convenient place. The initial kinetic energy is 0. The initial potential energy is mgr. The final kinetic energy is 1/2 mva squared. And the final gravitational potential energy is mgh. So I'll just substitute for all these values. I'm going to get mgr equals, for 1/2 mva squared, I'm going to write 1/3 mgh plus mgh. 1/3 plus 1 is 4/3, so I'm going to get mgr equals 4/3 mgh. Now observe the mass of the object cancels on both sides. Gravity cancels, so this can occur on any planet. And this gives us the answer we seek, which is h upon r equals 3/4. We have solved the first problem. Let us solve the second one next. The procedure is exactly the same in all these problems. In second one, you want to find something important at the beginning, which is the height from which it needs to be released. This, by the way, is used in circuses, where stunt bicyclists start from a certain height, goes upside down, and things like that. What is the safest height for the circus stunt? The data is again provided by the topmost point. At the topmost point, we need to have the free body diagram with the normal force acting down, because the cyclist is upside down, and the weight also acting down. And the result of both of these is that there is a centripetal acceleration towards the center of the circle, which I wrote there because I didn't have space over here. Let us apply Newton's second law first. Sum of all the forces, this is part 1 of that problem, in the negative r hat direction at point A equals m a sub c at point A. So I get mg plus the normal force at A equals mva squared upon r. That tells me that va squared, what's that going to be? When it barely makes a loop, the normal force is going to be 0, because that's a condition of barely making the loop. So that gives me, with mass cancelling on both sides, va squared equals rg. Alright. This mass cancelling on both sides is very important. It means that the details of the cycle and the rider don't matter. Our next step is to write the total mechanical energy at the initial point, which is the point of release, is equal to the total mechanical energy at point A. Ki plus ugi equals Ka plus uga. Initially it was at rest, so 0 plus mgh is equal to 1/2 mva squared plus mg times 2r. Now va squared is rg, so we can substitute for that. I'm going to get mgh equals 1/2 mgr plus 2 mgr. 1/2 plus 2 is 2.5, which can be written as 5/2. So I'm going to get 5/2 mgr. If you look at the leftmost side and the rightmost side, you realize that mass can be cancelled, mass independent, gravity independent, so this works on any planet. And so I get H equals 5/2 R. Let's go on to the second part. For the second part, we need to draw another free body diagram at the bottom of the loop. I don't want to clutter up this diagram over there, so I'll do it separately here. At the bottom of the loop, you're going to have a normal force at B. You're going to have mg, and I make the normal force bigger because I want the centripetal acceleration at B to act towards the center of the circle, which is now above point B. Let us apply first energy conservation to find the speed at point B. To apply Newton's second law, you need the speed at point B. To find the speed at point B, you have two options. You can either use energy conservation between the points A and B, or energy conservation between the points initial point and B. I'll do the initial point here. TMEI equals TME at point B. That gives me mgh, which is the total mechanical energy at point I, equals, there is no gravitational potential energy at point B, so there's just going to be 1/2 mvb squared. It's all kinetic. I like to think of this as potential completely being transformed into kinetic sometimes. So I get mg times 5/2 R from here is equal to 1/2 mvb squared. I can cancel the halves, and I'm more interested in Newton's second law rather than finding the speed, so I'm going to write this as mvb squared divided by R is equal to 5 mg. So I've taken R down there. Okay, now let us use Newton's second law. It says the sum of all the forces in the negative r hat direction at point B equals m times the centripetal acceleration at point B. So I get nb minus mg equals mvb squared over R, which is 5 mg by the work above. So this tells me, adding mg to both sides, that the normal force at B is 6 mg. So we have found the second part of the answer of the question. The last part involves the object here. So we can draw a little free body diagram. The force of kinetic friction, there's mg, there's a normal force, which I'll just call n, and that's it. So there's going to be a acceleration in this direction, but we want to solve this using energy. So what we're going to do is use equilibrium in the y direction, which tells me that n must be equal to mg, and then force of kinetic friction is just mu kinetic times the normal force. We're going to use those ideas to solve this problem. Okay, let's do that. The work non-conservative, this is the form of the energy conservation we have to use. Non-conservative work is change in kinetic plus change in potential plus change in kinetic. The change in potential, it's just come down that big ramp, so the change in potential is final, which is 0, minus initial, which is mgh. In other words, mg times 5/2 R. The change in kinetic is 0 because the final point B prime, that we are applying it between the initial point I and the final point B prime. At B prime there's no speed, at initial there was no speed, so it's 0 minus 0. And that all should be equal to the work done by friction. The work done by friction is the force of friction dotted with displacement. Displacement is in the forward direction. That's a displacement vector. So the force of friction dotted with displacement has a cosine of 180 with it. So that gives me a negative sign. Force of friction, which is mu kinetic times the normal force, that's mg. And then the total displacement, which is 3 times r, according to this problem. If you look at the left side and the right side, once again mass cancels, gravity cancels, and what I'll end up doing is bringing this radius cancels. so it doesn't depend on any of these things. And I'll end up bringing the 3 downstairs, so I get mu kinetic equals 5/6. The final problem, last and final problem, involves this hemisphere. The exact same ideas have to be used as in the previous parts. So what I'm going to do now is be a little bit colloquial about energy conservation. Wherever it's flying off, let's call this the final point F and at the initial point I, wherever the mass m is flying off, the loss of potential energy is going to be equal to the gain in kinetic energy. So let's write this. The initial potential energy was mgr, and the final one is this height, which is r cosine theta by trigonometry. So the loss of potential energy is just mgr minus mgr cosine theta. And the gain in kinetic energy, let's just call it 1/2 mv squared. That's our first equation. Now we have to apply Newton's second law at the point where it flies off. Let's call this normal force. That's mg. And that's the centripetal acceleration, a sub c. The component of the normal of the weight in this direction, since this is also theta, is going to be mg cosine theta. So rather than draw a force table, I just did what I needed there. So the sum of all the forces in the negative r hat direction equals mac is Newton's second law. So I'm going to get mg cosine theta minus n equals mv squared upon r. Now for it to fly off the ramp, the normal force has to be 0. Let's call that equation 2. All I would need to do is put 1 and 2 together. So let me put, instead of mv squared, I'm going to put mgr cosine theta over there. So I get mgr times 1 minus cosine theta from equation 1 is equal to 1/2 mgr cosine theta. Observe that mass cancels, planet independent because g cancels. It's also radius independent. So I get 1 minus cosine theta is equal to 1/2 cosine theta. And solving this, 1 equals 3/2 cosine theta, or cosine theta is 2/3. Now I know that cosine of 45 is 1 over root 2, which is 0.71, and cosine is a decreasing function, so this should be a little bit bigger than 45. You can figure out what it is using a calculator.